So next up, we have Samuel Mendoza Jonas, who will be talking about how the last 4 years with Petitboot have left a positive feedback at IBM Power Systems, right?
That's right.
Okay. Yeah. So give him a warm welcome and a round of applause for Samuel.
Thank you very much. I'm assuming you guys can hear me. As I said, just a quick bit about who I am. My name is Sam, obviously. I work for IBM in Australia, and trust me, I am filling every single one of the 36 hours to get here. I work in what's called the OSLabs team, which is part of the Linux Technology Center. And a lot of our work is getting Linux and stuff like that, working on the power architecture, so enablement, bring up, that kind of thing. I'm an Opal software engineer, which is the term I will explain a bit later, and I'm the maintainer of the Petitboot project. So what is Petitboot, though? When I started about 4 or 5 years ago, I had no idea at the time, and if you Googled for it, the first result you got was actually a blog post by Jeremy Kerr for a bootloader for the PlayStation 3, which is cool, but the only PlayStation 3 we had in the office was in at least 5 different pieces and did not work. So why did we care about it? So around this time, IBM was gearing up for its new Power 8 processor line, as well as something else new. Traditionally, most power machines, especially servers, run everything under something called Power VM, where your Linux, for example, doesn't run directly on the hardware. Everything is technically a virtual machine, to put it very simply. But with Power 8, IBM introduced the concept of open power, a certain line of servers that would run Linux directly on the hardware, which is great for fairly obvious reasons. More direct control of the hardware enables us to use technologies such as KVM for virtualization, that kind of thing. But the big draw card especially was that this was a completely open source firmware stack. If that will go, there we go. Very simple diagram here just to kind of explain the differences though. So on the left-hand side we have roughly what the old stack was. SBE is a self-boot engine, and hostboot is a fairly large layer of the firmware stack, which does early things like CPU setup, memory initialization, that kind of thing. And then you're straight into this Power VM hypervisor kind of thing, which then goes on to run these logical partitions, is what they're called in that particular context, but essentially virtual machines. And this new stack, the open power stack, same lower things that have now become open source, led into what we call SkiBoot, which is a small layer which essentially does a PCI setup, peripheral setup, console setup, that kind of thing. And then we want to go directly into Linux, but we don't really have a bootloader that we could use already, that transfers. So we need something new, and we can't use anything from the old thing. So what do? Thus, Petitboot. If you boot up an open power server, unless something's gone horrifyingly wrong, this is what you usually see the first time. Petitboot isn't open power specific or anything. There's nothing inherently power specific, but and you could even build this as a UEFI payload if you want. But sorry, actually I'll rephrase that. So while I've been working for Petitboot for 4 years, roughly, thus the title of the talk, the first Git commit is back in 2007, and there's a few people here who have used it before. Way before I started using it. So it's been around for a while, but with its use on open power servers, its use has really exploded in the past few years, and there's been a lot of changes since then. Petitboot is an approach to an open bootloader that plenty of us by now, especially after this conference, we're very familiar with. It's a set of small user space components, in our case mostly written in C, to find and boot Linux images, device setup, that kind of thing. We use kexec to boot into the next stage, into Linux or your FreeBSD example, anything that actually supports kexec. And then built into a Linux kernel user space, which we built a build root. In open power context, we call this image skig root, but essentially it's a small layer of changes on top of build root, and anyone could build this really. And we use a trimmed down version of kexec called kexec Lite, which is much, much smaller than the usual kexec tools, that kind of thing, just works for us. Tick. Another very simple slide, just to kind of give you a comparison where we sit close to x86. I was going to say it's early magic for x86, and then into normal UEFI layer, and you say your grub bootloader, and then Jonas. Similar kind of thing here, except we have our open firmware stack, and then Petitboot is kind of occupying the same space as, say, your grub, or if you think of Linux boot in your uroot kind of area, kind of thing, and then ski boot, host boot, bit of a grey area, and where Linux boot UEFI changes, that kind of thing. Petitboot itself, the tools are made up of two core components. We have this PB Discover server process, which manages devices, finds and boots boot targets, and does all the heavy lifting for device manager, that kind of thing. It finds boot targets from the disk, from the network, or manually setting up things, what have you, and then boots KZEC. Then on each interface, we have what's called Petitboot NC, which is what you saw originally, just before, which is the encoded front end that you run on every interface, so your VGA display, your serial console, your IPMI console, that kind of thing. And then a few small helpers to set up the console, set up the network, some device tree magic we do on power, that kind of thing. But in general, the rest is builder, it's BusyBox, it's all generic tools. At its core, Petitboot essentially mounts all the devices you have in the system and searches a variety of known locations for bootloader configurations from stuff like grub, yarboot, kboot, a few other options like that. And it parses these and presents them to the user. This is an example. This is from a grub config. It's parsed all the important bits, and you can modify if you want, but essentially that's what it would use to then KExec this device, or this boot target, sorry. Petitboot does have its own simple format as well, but the idea here is that we don't need to change anything in the distro. We just inherit the configurations that people are already using in their Linux distros, and then it's all good to go. NetBoot's also pretty straightforward as well. By default, let's configure it differently. Petitboot will DCP on an instant interface, searching for boot configurations via Pixie Linux, and a little bit of iPixie support, but it's pretty preliminary at this stage. There's no Pixie second stage required, like some other bootloaders we've seen, just like some other bootloaders we've seen today. Because we're already running Linux with KExec, we can just boot these targets directly, we don't need any second stage. Petitboot does the parsing and the booting, but everything else is generic BusyBox tools to do the DHCP configuration, all that kind of thing. There's also a little bonus mode we can have where some people are like, oh, I want to set up a machine with a static configuration, but I still want to automatically netboot. So we have this thing where you can set up your interface however you want, provide a path we can search for, and we'll just do normal Pixie Linux searching on that path. There's a number of ways to configure automatic booting behavior. Your normal stuff like boot device priorities, timeouts, IPMI overrides, which is something you usually see in more server deployments kind of thing for remotely configuring what you want to boot. This is fairly fine-grained. You can filter by generic device type, so like any USB device, or certain partitions, or even individual LVM volumes if you can find them on the system. And so, in a way, Petitboot's quite similar to some things we've already seen the past 2 days, like uroot and system boot and Linux boot, all that kind of thing. But if I had to kind of say why our approach is different, I'd say it's lucky in our sense, in that other projects like Linux boot are trying to open up this closed platform and give you options to do what you want on those platforms, whereas we're lucky enough that platform is actually already open, and we don't need to spend all the time there, so we can spend more time on providing a solid bootloader interface and tools and configuration, not only for individual users, but also for larger customers and ODMs who are saying, oh, I'm buying 1,000 of these, how can I fit it into my infrastructure, that kind of thing, making sure it works transparently, easy, and that kind of thing. So I said things got more serious around 2014 when we started doing this on OpenPower, and where has Petitboot been used since then? Oops. So I mentioned the OpenPower line of servers in 2014. So every OpenPower Power 8 machine is running Petitboot as its bootloader. First on the Power 8 S812L, which is technically not OpenPower, but runs the Opal stack. And then onto the rest of the Power 8 lineup, like the S822LC series. You might know of these as your Minxies and your Firestones, the OpenPower series machines. This also includes partner machines like Rackspace's Power8 Barrelline, which is their open compute server, as well as, for example, Supermicro have their Briggs & Stratton series of servers that are on Opal, or the Open Power Stack, I should say. This year, IBM launched its Power9 series of chips, in particular the Witherspoon and Boston machines, also known as the AC922, if you've heard of that. These are all open power, so of course they're in Petitboot as well. And you've probably heard that these are the compute and storage nodes on Summit and Sierra, which are the United States' two new supercomputers that took out number 1 and number 3 on the top 500 recently. Getting away from huge server stuff, the Talus 2 from Raptor Technologies is also a open power machine running a Power9, but much more, is pretty much our own example right now of having in a desktop workstation kind of form factor. All right, I'm pretty excited because we're going to get some of these in the lab soon, hopefully, if we can get them shipped. I know some people here are trying to get their hands on these. If you have one, come talk to me because I'm super interested to know what they like to use and how Petitboot works in a more desktop sense rather than a giant server deployment. And I hear cool things from elsewhere as well. There's a company called OpenGear. They do network gear, infrastructure, that kind of thing, based on x86. And they have been using Petitboot as the bootloader for their network gear, switches, that kind of thing. And they've been, which is cool just because it's on different architecture completely, but it's also cool because they've been extremely strong contributors to the Petitboot project, making changes, asking questions, everything. They're really active on the mailing list. There's been more, in a similar way, there's been more interest in running it on ARM64 and supporting EFI variables, that kind of thing. I'm not sure exactly what these people are using it on, but they've been very involved in the mailing list and contributing patches to make it work in a generic sense there. Another cool example for us personally in OpenPower is that because it's a small Linux image, fairly easily runs in our simulators when we're doing chip bring up and that kind of thing. Petitboot kind of ends up being one of our biggest debug tools. If you can get to Petitboot, you've done pretty well to get the new chip working. So why did we double down on Petitboot though and make it our main bootloader for OpenPower? There's a few reasons that come into play for us. Number one by far is that it is just Linux underneath it all. Not only does it mean using a lot of existing tools, but there's a lot of overlap with what our team does, is making Linux work on Power, enabling it for new chips, that kind of thing. So we save a lot of time doing both at the same time. Especially considering device drivers. Aside from platform support, there's a bunch of disk network, sometimes video drivers that we need to have in our bootloader stage. As you saw before, the old stack was completely closed source. Can only bring so much stuff over from there. We didn't really want to, no one in the team really wants to rewrite all the, say, OpenFirmware 4th drivers, and even considering UEFI generic drivers, even if they do exist, they don't tend to run on Power anyway. So picking up Linux is way easier in that sense. It's open source, which goes very well with the open firmware idea, obviously, but not only that, it's very easily to extend, both for individual users and for when we're talking about extending it for the, larger ODMs, that kind of stuff. For the machines we're running on, we have generally more complex requirements than just boot this on this disk, or whatever happens to be on the network. So it's important for us to have a platform we can easily extend. The internal structure of Petitboot on a programming level is such that it's pretty easy to adapt to multiple platforms and to variants of those platforms, which is great for us because we have, say, 3 or 4 different variants of a Power machine, and also I've already said these people running on x86 and ARM as well. It's fairly intuitive. So we have a lot of users coming from a traditional x86 environment. They come in to use Petitboot, and they might have a few questions to start with, but then generally they don't come back. They're good to go. Everything's fine. We're not finding too many teething problems with that. And as mentioned before, it's a drop-in replacement because we don't have to tell the distros that people are using Petitboot on this new OpenPower platform. It just automatically works, which is great for us. So basically, your Linux off bootloader has a lot of advantages and some disadvantages, but some of the advantages are, as I briefly mentioned already, just the huge amount of tools and infrastructure that already exist, and then we don't have to rewrite everything with a limited amount of manpower. Especially with this, because there's a huge community around this, we can trust that these tools probably work, and even if they don't, we're not the only people trying to fix them. So there's a lot of community support making everything work. We have, so the ski root layer, which is our Linux image, is a thin layer of additions on top of a normal build root. install. And even then, most of that's actually in creating our other firmware images in a flash format we can flash on a machine. The actual additions that we have for building Petitboot are tiny, especially with the kernel. We are so thin that we run a completely upstream kernel except for one patch, and that's just to get USB 3 working over KExec. It's a good opportunity to give a shout out to Buildroot, just because they're a great team to work with and make using the tools really easy, and they're very active in talking about contributions, and are very nice when we have weak contributions, that kind of thing. Oh, not too early. Additionally, I said obviously there's a lot of overlap with our kernel enablement, but we also spend a lot of time making sure that Linux is just nice to use on power. People don't have a lot of transition pain, that kind of thing. So using all these normal Linux tools in our bootloader is forcing us to spend time making sure everything works nicely. Because it is Linux, it drops to a real shell. There's no restricted environment where you have a dozen commands and you hope that's enough. It's completely Linux. You can drop to a shell, do whatever you want. I've even seen examples of people, especially the guys using the Talos machines, dropping to a shell and entering a chroot into the Gentoo installer and just installing it that way and skipping the whole installation process. And so not writing all this from scratch frees up a lot of time to do new things and use these tools in new ways. One example is the device mapper snapshot framework. Petitboot mounts everything read-only because generally we're only reading configuration files, except for a few small examples. But read-only is not always read-only. For example, if you shut off a machine with the dirty file system, you come back up, Petitboot tries to mount that file system, does some recovery, those fixes, the file system fixes, are written back to the disk. Normally that's totally fine because you do want your disk to be in a good state. But earlier on we were much more paranoid in saying, well, what if the file system drivers got a bug in it, or we messed something up when doing our parsing, that kind of thing. How do we make sure that us, the bootloader, are not responsible for just trashing this whole machine? So to do that, and this is just drop to the shell and Petitboot and rod mount, as you can see. What we do is for every device that Petitboot would mount, instead of mounting the actual device, we make an in-memory snapshot of this using device mapper, and we mount that. You can see these all dev mapper something. Don't mount the actual device. So any writes that do happen to the device, go to the snapshot, and you can sync those back to the real device if you want to, but it must be explicit. And in this way, we avoid this kind of problem. There's probably only been 1 or 2 times I've seen an issue where this saved us from ourselves. So mostly it's making me and some other developers sleep better at night. But it's a cool way to have in there for pretty zero cost, all things considered. Now that we're seeing more desktop users, it might need slightly better UX, user design, just because people have now gone to the shell and gone, oh, I made a bunch of changes and nothing happened. They're like, yeah, we stopped you doing that, isn't that great? And they don't always agree. So we need some way to make it more obvious what we're doing there. So there are some disadvantages to doing Linux this way. There's all these great tools, infrastructure that we're using, and so we now have a dependency on these tools that are not owned by us, which is fine, but they have their own communities, their own motivations, their own road paths for changing stuff. And so changes to these tools come down the pipe, whether it be bugs or incompatibilities or changes we weren't ready for. It could generate a lot of work. This is kind of by design in a sense. We try and stay upstream as much as possible so we catch this kind of thing early, but it does generate a lot of work trying to control all these tools that we don't directly control. A KExec-based bootloader is while I do it almost 3 times, while I boot something KExec almost 3 times a day, I'm sure probably people do here as well, it's not actually probably the most common use case for what you're doing with Buildroot, and particularly concerning KExec. If I had to guess, I'd say the biggest user of KExec is probably actually kdump, which if you're not familiar is a tool you can use in your Linux distro where if there's a catastrophic failure and everything blows up, you KExec into this very limited crash kernel, save some information, some dumps, that kind of stuff, so you can analyze what happened. The problem with that is most device drivers, when KExec happens, are expecting something like a kdump event to have occurred. So they don't really care what happens after that because the machine's already kind of going down. There's not a lot of care taken to what that means for a device, or the device driver in particular. And historically, this has meant a lot of cases of pressing boot and the machine just completely going down in flames because some device driver has not handled this event. It's a lot better these days, but you still occasionally see it come up if you try a new device over KZEC and it doesn't handle it, and there's some work there to make sure everything works okay. An even smaller use case potentially is a KZEC-based bootloader on power. A fun bit of trivia is that power machines can switch their endiness at runtime, and they quite often do. Not everyone is really expecting us to do that though, which has had some fun issues, especially again considering KZEC. There were some issues where, first the KZEC, there was an issue with the file system, for example, where Linux was running, the file system was unmounted uncleanly, the machine rebooted, came around again, so there's a dirty journal, and Petitboot mounts it in the opposite endian that it was written in, and the file system really cared about that. We had to do some work to figure out what the hell happened. Another example of KZEC was when we first started to do this on OpenPower and switching to little endian, is that say if your Petitboot layer was running little endian with KZEC, your CPU 0 would switch back to big endian, because that's the architecture default, but all your secondaries were still in little endian going to the next kernel, and complete disaster. Most of that was early teething issues, but it's just an example of what you see when you're not running the most mainstream stuff. Other examples, if you're familiar with a KZEC file load system call, which is an effort to make KZEC more secure, that was a lot of work went into that recently to give it PowerPC support or power support, but it doesn't support loading in KZEC with your own device tree, which is something we do a fair bit in Petitboot, so we need to spend some time working out a solution to that, or an alternative. So working close to upstream is great for development and maintenance and catching all these things early, but we do occasionally actually release firmware on these machines, and they're not running Petitboot master or an RC2 kernel, that kind of thing. We do stabilize occasionally. But because we do have several varieties of power servers running at different levels, that kind of thing, we don't in Petitboot want to guarantee exactly what kernel or ABI or everything you have underneath. Because there's just not a strong need for that, and it's easier for us if we can stay close to upstream all the time, always be iterating. But where it has caused an issue in the past is something with device setup utilities. So some vendor has a RAID card that we include in our server. There's some tool they use to configure that, usually in Linux, that kind of thing. But because Petitboot is Linux, we can now do this before installation and everything, which is great. And people are like, oh, it's great. So vendors and even some users are like, oh, when can we include these tools in the Petitboot image and save some time there? And there's two big reasons we didn't want to do this. Number one is that they are almost exclusively closed source blobs, and we don't really want to be carrying that in our image. And number two is that they tend to have a fair amount of dependencies. And if we suddenly have 4 firmware streams, all running different devices, that kind of stuff, we don't be holding dependencies for all these potential tools that we might run in our limited amount of flash space, which is only a dozen megabytes or so. So the solution we have for this is something called PB plugins, or Petitboot plugins. My colleague Jeremy Coe did most of the core work for this to define the ABI. I've been spending a lot of time trying to blend it into the UI, making it more automatic and transparent to the user. It's not a particularly complicated process. What a vendor can do, or whoever wants to package a tool up, is compress the directory in a CPIO structure with all the dependencies and everything you need, and just a thin layer of metadata in there to tell us what's going on. And then Petitboot, or its PB plugin tool, will take that, install it to temp, transparently set it up so if you call the command that's held in there, Petitboot will chroot you into that directory and run it from there. This is great. We can run these tools easy. We don't have to distribute them. All the dependencies are there, and they're not going to walk all over the file system while doing it. Petitboot can automatically scan the disk and network for these PB plugin files at the same time as looking for boot configurations, and then present these in the UI. You can see here, there's one here called arcconf, which sets up a storage controller. There's some metadata there to tell you what exactly you're running, and from the UI you can run it rather than digging through the shell and trying to figure this out yourself. We're spending time making sure this is transparent and easy to use while letting us not distribute it ourselves. I've said a lot about this is good for vendors and that kind of thing, but the same concept applies to any debug tools you want to package up or any additional features you want to add to your Petitboot installation. You can wrap up as a PB plugin. Didn't quite have time. I was going to do a thing where you packaged up Zork or something and write it in your bootloader transparently. It would have been fun, but anyway, exercise for the audience. But now seems like a good time to talk about security, potentially. Back in 2014, we were really just on, does it boot anything? And now in 2018, it's much more about, our users want to know, is it booting what it is meant to? Another rough slide. So there's probably two major bits of this, depending on whether you're looking at Petitboot or whether you're looking at the OpenPower stack as a whole. You can see the lower end, everything, all the stages up to Petitboot are covered by OpenPower Trust and Secure Boot. And then we have some things going on in Petitboot as well. So the Opal Secure and Trusted Boot thing, I won't go into this too much because it's another team's work and I don't work on it directly too much. But on most OpenPower machines, you can implement Trusted and Secure Boot, Trusted with the attached TPM, and Secure Boot to verify the signature of each stage as you load things from Flash up until you get to Petitboot. And by the time you get to Petitboot, you can be fairly sure you're running the Petitboot you intend to. Then in Petitboot, we can support signed and encrypted kernels. Also, boot images, which includes your kernel, init, boot arguments, even your device tree, you can sign and encrypt if you're running on power and doing that kind of thing. This works on both local disk options and for the network. And the best bit about this, for me personally as Petitboot maintainer, is this was 100% outside work. The original GPGME support was written by Raptor Technologies for their first Talos machine, and then the company I mentioned earlier, OpenGear, came in and extended it to support OpenSSL. That work includes a lockdown kind of mode to secure the UI and make sure people can't drop the shell on anything, that kind of thing. You can also boot most encrypted installations. Petitboot doesn't quite support encrypted boot petitions just yet. There's not a lot of work to do there. It's just on my to-do list, essentially. But extending that concept of locking down the UI, something I'm working on is working out how we can tighten up what the various Petitboot components can do. Traditionally, everything running in this Linux image is running as root, just because it was easy at the time, but it's really not required, and especially if you attach say in these machines you have a BMC providing a remote IPMI interface, you attach this to the internet, which you really shouldn't, but people do, that kind of thing. There's a remote interface directly with root essentially into this machine. So there's improvements we can make here. So what we've done is, because it is just Linux, we've just made it so only the PBDiscover server process runs in the background and manages devices and does the booting, has root privileges, and everything else is a completely unprivileged user. So that includes the UI, some of the setup tools, and especially even if you drop to the shell, you're just an unprivileged user. Unless you actually know the root password for this machine, you can't do anything. And on Power, we store the password hash in NVRAM. That could be extended to do things with TPMs, that kind of thing, or depending on platform. This is great because it solved the feature request for hardening the UI up a bit and adding passwords and that kind of thing, while just leaning on the existing Linux infrastructure, which has a lot more eyes on it than some other things do. Especially means I don't have to make sure my ncurse's code is super robust, stop people getting out of it. Just say, you can get out of it, that's fine, you're just an unprivileged user. Patches for this are up on the mailing list if you're curious. Reviews always welcome, as well as bike sheds. So what is next in the future for Petitboot? Like I said, we're extending that PB plugin support to be more transparent, extend the ABI to make it more flexible for certain tools and add more parameters, that kind of thing. We want to try and get automatic ISO image installs working. There's already patch on this for this that kind of work. For example, if you're installing a Rail netboot image, you can boot from that ISO and it will work and you can go on. But if you have an installer that requires accessing what's on the ISO in the installation image, that doesn't work because the ISO has disappeared because you ksect. So we're playing with ways of reserving the ISO image in memory so it appears as a block device in the next stage. Trying to do generic firmware updates in Petitboot via a nice interface. Most of that is actually up on the list as well, but like I said, we have a few machine variants, and associated with that is about 5 different ways of updating a machine at the moment. So I'd like to try and bring that together, make it a nice example before we merge the whole thing together. And more stuff like that. Different interface types for, say, a user working on the desktop machine compared to a machine running in a data center, where you only want to care about the status and that kind of thing. You don't really care about interacting with it. extending testing and that kind of stuff. Petitboot's got a lot of in-tree static testing and that kind of thing, but we want to do more stuff with QEMU. There's something in the OpenPower thing called OP-Test, which does a lot of extreme firmware testing on different machines, that kind of thing, and that supports QEMU, so we can just put Petitboot into that, include it with their testing effort, that kind of thing. Crazy stuff like, what if someone attaches 10,000 disks to a machine? Will Petitboot deal with that? The answer is QEMU dies way before then. But it's a way of stress testing what we can do with that kind of thing. So if you're interested, please get involved. The home of Petitboot is on oslabs.org. We also have it's also on the GitHub OpenPower organization. The trees are exactly the same, we just tend to use it for issue tracking and that kind of thing. And the mailing list is there. If you're interested, come have a look. I think that's about it. Thank you very much.
Thank you, Samuel. Are there any questions?
I'm very interested if you can go into some more detail about what the earlier stages in the bootloader are doing for security, how they interact with the TPM, and also what sort of flash protections the Power 9 has to prevent malicious or unauthorized access.
I can a little bit. Ideally, my colleague Stuart was going to be here this week and do a talk on that actually as well, but he couldn't make it. Actually, maybe sure if Ben is there, do you mind know much of the stack? Just to single you out. Yeah, I'm not sure about that. The trusted stages, I don't know as much about, because it's a different team, like I said. The secure bit stuff, in Flash, all the firmware stages are laid out more or less roughly as I was saying before, and each one of those is wrapped in a secure container with a certain secure header on top. And then that is, as the machine boots up, those signatures are checked. As each stage checks the next signature before it comes up, that kind of thing. I probably won't go too much into it there because I'll start explaining things the wrong way, but I can get in touch with some people who do know much more about this if you want.
Okay, any more questions?
Hey, my name is Dimi and I have a question about, you said multi-platform support.
Mm-hmm.
For example, if you would like to have an infrastructure, or let's say we support different, different scenarios where we have Power 9 and at the same time we have an 886 system, and you mentioned something about having other platforms. So how much is Petitboot supporting other platforms than Power 9 currently? For example, if we take the Linux boot and we want to, let's say, use a supported Intel server board there, they have the 2600 WF, which is modern enough, let's say. So, and then we want to have the single bootloader. We don't want to split and support two different bootloaders. I mean, do you think this would be possible in the near future?
Definitely. I mean, the vast majority of Petitboot is platform agnostic. Most of the platform-specific code that we have is stuff from generic stuff. Is stuff like, say, on this parallel platform, how do we do it? How do we figure out IPMI? What
config.
consoles do we have? That kind of thing. Yeah, or where do we save our config, say, in NVRAM or an E5 variable, that kind of thing. So the only extra work would be just working out how that works on a platform. It's fairly easy to add, but you could probably take it as it is, and 90% of it would work fine.
Sounds great, yeah, because I think it's really good if we can just focus on one bootloader. I mean, it will lower finding the problems in the booting procedure afterwards. Once we get away the board specifics and we can get the secure or trusted boot, we can have something very similar rather than having different scenarios. And I see a lot of movement. I mean, we see the Linux boot progressing, we see the Petitboot. So if it's really that much hardware agnostic, it sounds really good. Take a look. Thanks.
Okay, any more questions? Okay.
I know that Petitboot had a graphical interface instead of the ncurses interface.
I was wondering who was going to mention that, yeah.
Are you going to bring it back?
I've played with it a little bit. The biggest thing is kind of fallen out of use. It is in the tree still, but it's fallen out of use a bit just because the main interface on most of our power machines is IPMI, so we're kind of constrained to the ncurses interface. most of the code's still there. It probably just needs a bit of TLC to get it up to date with everything else. And we need to do some work on the VGA console setup more than anything else. But yeah, potentially we can bring it back, especially if people are using it in a desktop scenario. Might be a little nicer, so yeah. I was trying to be optimistic, but yeah, there's a bit of work to get it up to date, essentially.
Do you need the mic?
I wrote that stuff, and it was just an excuse to play with the twin library that Keith Packard wrote back then. Even the font handling in that thing is absolutely horrendous. You take a TrueType font and you transform it into a series of Bezier curves, and then we render that manually. You really don't want to reuse that interface, believe me. If you want to do graphics, the main problem is going to be having a way to easily abstract the various forms that Petitboot has for configuration of IP, for example, or boot device, etc., etc. That's all based on end cursors, and you would have to, I don't know if we have any abstraction at the moment in there, but you definitely would need some, and you would need then to implement a graphical variant of all of that stuff, at which point you probably want to start looking at existing graphical libraries rather than reuse the crap I have in there. It was a toy. In the context of the PS3, I think we had to fit the entire thing in 4 meg of flash, which is why it made some amount of sense, because Twin is very, very tiny. And we had no network booting, no options, nothing. It was just looking for distros on the disk and booting them. But honestly, we wrote that during conference evenings and probably not sober. I wouldn't recommend using it as a starting point.
Thank you. Any more questions?
So I was interested in your, sort of this whole secure boot thing with the keys and all. So in the Power implementation, where is sort of the root key kept? Is it in fuses, or is it in somewhere rechangeable?
Again, I need an asterisk to it. This is not my work, so I can't answer that.
It
But
really-
I believe it is. They're fused in at vendor time. Oh, Ben,
Here's
do
the
you
reason it matters.
I don't know if they're fused. It's a vendor.
Possibly you
thing.
can take this back to you. Again, the resale question keeps coming up, and the desire of a consumer further down in the chain from the first buyer to essentially rekey it.
Yeah.
And again, this is the thing Chromebooks really get right, and a lot of, let's just, to pick on it again, like the ME scenario gets wrong. So if there's any way to make that get done right, it'd be cool.
So I totally agree, but I'll probably find you someone who's more intimate with the secure stack to answer the question.
Okay, thanks very much.
Are there any more questions? So how big is the image of your init ROMFS? Or,
All right, so on pretty much all the Power servers, we reserve around 16 megabytes of space in flash for the whole image. That's kernel and NRFS. I think the kernel's 3-ish megabytes, and the rest is the user space side.
And how many developers are there?
How many what, sorry?
How many developers work on
Developers?
Petitboot?
Depends how you count. I'd be the main developer, essentially. But we get a lot of contributions from, like I said, Raptor and OpenGear are big contributors, but so are plenty of people from places like Red Hat and Ubuntu, extending into their environments, that kind of stuff. And there's a few people who don't work directly on it in the team, but know enough about it to work on it if they need to, kind of thing.
Okay, we have time for a few more questions. So, anyone? No? Okay, thank you, Samuel. Give a round of applause, please.